Good evening, everybody. Good evening, everybody. This is Lorenzo Perella from Physics 116, Clark Wellman's class, to talk about the second lab. Today is discussing about a ball bearing in a styrofoam cup that's the shape of a cone, and seeing how much water is displaced from that when it bobs down. And now, as in number 5 and 6 state, if the large container has a cylinder of 10 centimeters, what is the change in level of water in the large container when the 3 centimeter diameter ball is moved from the inside of the cup to the outside, which is this case being the water? Does the water level change when the container goes up or down when the ball bearing is removed from the cup? Now, in order to get to this part, we first have to go through the calculations. We initially start here. Now we use the volume of water displaced from the ball bearing. And to figure this out, we use Archimedes' principle, illustrating that the buoyant force is equal to the weight of the fluid displaced. Which is the same thing as the buoyancy is equal to the mass times gravity, or the density of water times the volume of displaced of water times G is the density of the steel ball times the volume of the steel ball times G. From there, we get that 8.05 E3 kilograms per meter squared times 4 over 3 pi r cubed times 10 meters per second. And we know that the radius is half of 3 centimeters, which is 1.5 e minus 2 meters. And if we cube that level, we get 3.375 e minus 6 meters cubed. Afterwards, we see that we take the density of water times the volume displaced is equal to so forth as density of steel times volume of the steel ball. Once we do those calculations, we end up with a volume of water displaced to be 1.138 e minus 4 meters cubed. But then we find out that the volume of the ball bearing is the same as the volume of water displaced when the ball bearing is thrown overboard. To get this, we simply just need to find the volume of the sphere. We take our radius and take that to the third power, multiply that by 4 over 3 pi, and we get 1.414 e minus 5 meters cubed. Now we've reached this number 5. Now we have this cylinder, and we are trying to see how the height changes. Now in order to utilize this, we need to use those numbers that we just went over from numbers 3 and 4. And to do so, we take the answer from number 3 and subtract it from the answer number 4. What we find is that the change in volume is 9.9667 e minus 5 meters cubed. This relates back to how there are two forces acting on the cup. There is one force, which is similar to the buoyant force, and then, sorry. What I mean to say is that the force of buoyancy is equal to the second force, which is pushing up on the floating cup and ball bearing, minus the first force that's pushing down on the ball bearing and cup. And this is similar to the second height times the density times gravity by the area minus height 1 and density times g. And we get the area by taking 5 centimeters, 5 e minus 2 meters squared times pi, which ends up to be 7.85 e minus 3 meters cubed. And we find out the volume is equal to the area times height. So what we do here is take our change in volume times divided by area, and we end up with a change of height of 1.27 e minus 2 meters. This is a reasonable illustration because when you remove a ball bearing from the water, there's a large amount of water. Even if it is localized into a cylinder, the change in volume height is minimal because of the comparison of the water compared to the total area volume that is encapsulated. And then for number 6, we utilize the same type of idea. Now first, we try to see in this, when we have a steel cannonball of 25 kilograms in the lake of uniform depth of 10 meters per second, 10 meters in diameter, the volume of the cannonball is, again, 4/3 pi r cubed, and we know the density of steel to be 8.05 E3 kilograms per meters cubed. In order to figure out the amount of volume that there is, you take the density of the cannonball and divide that by the density of steel. I mean to say, the mass of the cannonball divided by the density, and you get 3.11 E minus 3 meters cubed. And that equals the water displaced when the cannonball is thrown overboard, as we've seen from before with the ball bearing. Whereas with the canoe, you take the cannonball's mass and divide it by the density of water, and you get 2.E minus 2 meters cubed. We find through a difference in volume there to be 2.189 E minus 2 meters cubed. And if we take that divided by the area of the lake bottom, 5 meters cubed times pi, we get 2.787 E minus 4 meters, which is the change in height. Now, as you can see from our illustration, when we first think of how if the mass of the canoe is massless, it will not affect the system. Originally, the canoe will just float on top with the ball bearing, and the canoe will rise without going down when the cannonball in this case is pushed overboard. However, when the canoe has mass, say in our mass 20 kilograms, even after the cannonball is taken out, we see that it'll still push down. Another problem that we're trying to answer from here is, you need to account for the mass of the boat? The answer to that is no. For while the mass does change it, we can see through our calculations that the height is still going to be the same, because the mass of the canoe due to gravity is going to cancel out. And in the end, you'll roughly get the same height of 5.45 E minus 4 meters. And that is relatively well done, considering all the error. And I might have messed up a little bit, but numbers do equal out in the end. Thank you for listening to the second lab. I hope you found it informative. Thank you, Mr. Wellman, again, and we'll see you next time.